Hello world and welcome. Today we'll talk about deep learning and neural nets, part 2. My name is Harris and let's get started. For more tutorials, hit the subscribe button or leave a like or comment there. I'll be really happy about it. So what are basically the comparison between machine learning and deep learning? You have in both cases a data set. At machine learning you have to select the features by yourself and then train a model, select the model, and then you have output. In deep learning you have just a data set, you just take a neural net and then you have output, a prediction. So the feature selection is removed this case. Deep learning is a subset of machine learning, and machine learning itself is a subset of artificial intelligence. For our neural nets, we need the neurons itself. This is the basic part of neural nets. So if you see that from a science perspective, you can imagine neuron is this different parts that you can see here, like the connection, it's called axon, dendrites, and the axon terminals who are connected to the next neuron itself. We can find it in our brain, and this is how we try to mimic it to copy this feature for our neural nets. But in real life, here we can see how the neural nets looks like. So if you try to put an artificial neuron, then you have basically input here who is connected to a neuron. Neuron is nothing else than a function, also covered with the activation function. Then you have an output signal. If you see a theoretical point of view of neural nets, you can imagine here you have an input layer, output layer, two hidden layers, and all the neurons, in this case 8 neurons, are connected to each other. So each of them is connected to each other. Then you have a bias, so it's kind of some output, some offset that is connected to each hidden layer, which you will sum up. And then you have a weight, which you can use basically to train your neural net. And in each neuron, there's a function or activation function. If you see this calculation, then you have here two input layers and hidden layer, output layer, and then you can basically multiply the input with the weights, in this case 0.5. You have a hidden layer, then you have the bias, so the offset itself. You can also take it to the calculation. You multiply it with the sigmoid function and then with the weight afterwards. And then your output will be only 0 or 1 in this case because you use the sigmoid function. And the math looks behind all this vector calculation and matrix and array calculation, that you have basically the x, so the input data, you multiply it with y, with the weights, and then all the sum you are kind of adding to the bias, so the offset, and if you have this function, you multiply it with the activation function. The nonlinear activation function that we are mostly using is a sigmoid or ReLU. So there's a sigmoid function, the hyperbolic tangent, then we have the rectified linear unit, the leaky ReLU, the exponential linear unit, and most cases in hidden layers, for example, we're using for the neurons the ReLU function, and the sigmoid function we use for the output layer in most cases. So how does the feature selection really works in real life? So you can imagine that a neuron is not always connected to each other. For example, you can see here a hidden layer, output layer, and input layer, and the neurons are connected to the input layer. And the first neuron is only connected. In this case, you try to predict the price of a house, and then you have a data set of different houses where you have the area of the house, you have how many bedrooms you have, distance to the city, and the age of the building, and then you try to predict the house price. In this case, you can imagine that you have an input where the first neuron is connected to the area, and also the distance is connected to the first neuron. And the second one is only connected to bedroom and to the distance to the city. So each neuron has its own specific features which it's going to use, and then it has as well different weights as well to calculate the prediction. And how does a neural net learn? Basically, you can imagine it's here like you have in the middle activation function, you have the weights, and each iteration the weights will be updated or adjusted. You are doing it by taking the output value, the y hat, and you compare it to the actual value. So if you have a 2 and a 0, and you have some kind of deviation in this case. If you can see the graph on the right, you can see that output value is not the same like the actual value, and the difference of it is the cost function. The cost function should be as small as possible, and by each iteration you try to adjust the weights itself here in the neural net, and you are kind of doing it each iteration, and after a while the weights will be on the minimum of the cost function, and it is the best fit. If you are adjusting the weights, you need the gradient descending approach. So you can imagine it like you push a ball downstairs hill, and then if it will land at the minimum of the cost function, then it will be the proper minimum, and this is the minimum of weight, which is the best fit in this case. So we have the gradient descent approach where we are doing this. As you can see here, you roll down the ball at the hill, and then you have basically 3 hits until it will reach the minimum. This is the minimum of the cost function, and this is the perfect fit for the weight. So the weight is pretty small. But if you have a lot of dimension, the cost function will not look like parabolic, it will look more like this. So if you have a lot of dimension, so you can't just have a batch of data set and choose it and adjust it after, let's say, 10 or 100 rows. You have to do it like each row. That's why you're applying the stochastic gradient descent to try, in this case, the minimum of this curve. If you compare both of this, here on the left you can see the batch gradient descent and the stochastic gradient descent. You can see that the batch is going to apply after 8 rows, and the stochastic is going to apply or adjust the weights each row, which is a better approach for nonlinear cost functions. In the middle you have something like mini batch gradient descent, and therefore you adjust the weights after, let's say, each 4 row, and then another time, so after many blocks. This is also an approach which we will also consider and see in the next examples. The backpropagation is actually there to adjust the weights itself. We had the forward pass for the neural net to pass the weights from one layer to the next, and then afterwards we calculate the loss function or the cost function. We derive the loss and adjusted the weights each iteration. This is called backpropagation. This is how the weights are adjusted, and this is how basically the neural net is learning. The optimizer you can basically use for adjusting the learning rates, let's say, and this is also an approach which you can use also to adjust the weight itself. Mostly we will use in our examples the Adam optimizer, because you can see it here on the x-axis you have the iteration itself, and on the y-axis you have the training cost or the loss itself. So you can see that Adam is pretty good as optimizer to have the minimum of the loss and to optimizing the weight itself. So thanks for watching. For more tutorial, please hit the subscribe button or leave a like or comment there. Thanks a lot and see you soon.